Okay, an important thing in the world of motion is the idea of forces, since forces are responsible for much of the motion that's out there. First of all, what is a force? Well, you can think of a force as being basically a push or a pull. It's something that's capable of changing an object's motion. And, since that's an acceleration, in other words, force is something that's capable of accelerating an object. There are two general types of forces. And one of those is contact forces. And this is one where a force acts directly on an object. In a way that we can observe it. I'll say in a way we can see. And an example of that would be an example of pushing or pulling something. If you walk up and start pushing on something, well, it's obvious to see how the force is acting on the object. The other type of force, though, is action at a distance type forces. And those are ones where the force acts in ways that can't easily be seen. And so action at a distance forces are the types of forces where the effects can be seen, but the force itself can't be seen. In other words, there's no contact between any physical manifestation of the force and the object that the force is acting on. And as you might suspect, one of the action at a distance forces is gravity, because you can't see gravity acting on something. You can only see the effect when something falls to the ground. Magnetism is another example of action at a distance forces, because you can't see magnetic forces at work either. And a magnet doesn't actually have to touch something in order to move it. Okay, so those are a couple of types of forces. There are what are known as four fundamental forces in nature. Some of these we're going to study in detail and some of them we won't, but we might as well know what they are. One of them is a gravitational force, which we've already mentioned, and we'll be doing quite a bit with that. Another is electromagnetic force. Electricity or electric forces and magnetic forces are linked to each other. So they're often combined together in electromagnetic forces. we won't actually be doing anything with those during this session because unfortunately we just don't have time. There's also the strong nuclear force, and that's what holds atoms together. Well, we haven't really done chemistry yet, so we haven't seen it, but the way atoms are put together really shouldn't work. Particularly, you should not be able to get all those positively charged protons into the nucleus together at the same time. They should repel each other. But the theory goes that there's this strong nuclear force that allows you to have all those protons within a small distance of each other. Even though they all have the same charges, they don't repel. And there's also the weak nuclear force. And that's what's responsible for radioactivity. So those are the main types of forces in nature. Gravitational forces are the only one on the list that we're really going to study in detail. And you know, that's enough to keep us busy for a while. There's also the idea of net forces. And a net force is just the sum of all forces acting on an object. And when we say net force, we mean that we're taking not only the magnitude of the force into consideration, but also the direction. So forces acting in the same direction add up. Forces acting in the opposite direction are basically subtracted or counteract each other. And then forces that are somewhere in between can partially add or partially subtract. That is, in directions that are, say, partially in the same direction and partially in the opposite direction, or acting like at an odd angle to each other. And they'll partially add or subtract. Okay, so variables for force would be a capital F, and the unit in the SI system would be the Newton, or a capital N. 1 Newton equals 1 kilogram meter per second, kilogram meter per second squared. It's a compound unit, and it's derived from several other units, and it's just basically as a matter of convenience that they decided to give this combination a special name, named after Isaac Newton, who came up with the basic laws of motion. And for simplicity, they just gave it one single name, so you don't have to keep saying kilogram meter per second squared. The reason that the unit for force is kilogram meter per second squared is that, well, as we said, a force is something that's capable of accelerating an object. Acceleration is in units of meters per second squared, and the main characteristic of objects is that they have mass, and the SI unit for mass is kilograms. So when you're measuring a force, you're basically measuring the mass and how much it's accelerated. And so that gives you a unit that's a combination of kilograms and meters per second squared. And in fact, you can look at the equation for net force, and it is F equals ma. For net force is equal to mass times acceleration, and mass is in units of kilograms in the SI system, and acceleration again is in units of meters per second squared in the SI system. And so out of that, you get kilogram meters per second squared. And that's what they chose to call the Newton. Okay, and the upshot of this equation is that no force is required to keep an object moving at a constant speed. Constant speed, remember, means no acceleration. So if, basically look at the equation above. If acceleration is 0, then it doesn't matter what the mass is. Anything times 0 is 0. So force is 0. Okay? So that's true. It actually doesn't require any, basically there are no forces required to keep an object moving at a constant speed. Now, that may be counterintuitive. You're probably thinking, well, that's not true. If I set a ball rolling across the floor, it's eventually going to stop unless I keep pushing it. Or, if I'm driving down the road and I let off the accelerator, the car is eventually going to slow down. It's not going to keep moving at the same speed. And that's true because here on Earth, we're dealing with things like friction and air resistance. Newton's law, and this is actually part of Newton's laws of motion. Newton's laws are set up basically assuming there is no friction or air resistance. And so without friction or air resistance, that's actually true. No force is required to keep an object moving at a constant speed. If you're in outer space where there's no air to resist your movement and no friction to slow you down, then an object, once it starts moving, it just keeps right on moving and moving and moving at a constant speed, essentially forever. And it was really pretty impressive that Newton was able 300 years ago to just imagine these situations that really don't exist here on Earth. That he was able to take an ideal situation and say, okay, if you eliminate friction and air resistance, this is what will happen. And he was right. Okay, so that assumes no friction or air resistance. Because with friction and air resistance, that would not be true. So in other words, 1 Newton would be the force required to accelerate a mass of 1 kilogram by 1 meter per second squared. So that's basically what the Newton is. Okay, so an important force is the force of gravity. And the force of gravity acting on the mass of an object is called weight. That's what weight is. Basically, weight and mass are related to each other, but mass is kind of an inherent property of an object or a sample. It's how much matter there is in that object or sample, while weight is the effect of gravity pulling down on that mass. And so weight is related to mass, but it's not the same thing. Weight will change with gravity if gravity changes, but mass will not. So your mass is the same on the moon as it is here, but your weight will be less on the moon than it is here because gravity is less. And so as a result of this, weight is a form of force. And the equation for weight is given as W equals mg. That is, weight equals mass times gravity. This is analogous to the equation for force, which is F equals ma. Force is equal to mass times acceleration. So we see mass and mass in both equations, and the other term would be g or a, which in either case is an acceleration. Gravity is a form of acceleration. Notice the units that gravity is measured in, 9.81 meters per second squared. Well, meters per second squared are units of acceleration. So gravity itself is an acceleration, and it results in a force that's known as weight when it pulls down on your mass. So as a reminder, mass is a fundamental property of matter. And mass is a constant for any given object or sample, unless you change the object or sample. You know, if you have a piece of metal and you hack a piece off of it, then the mass will change, although the total mass of all of the pieces will still be the same as it was before. And mass is the measure of the amount of matter in an object or sample. And the unit for mass would be kilograms in the SI system, or slugs in the English system, which is kind of an interesting sounding unit there. But we don't use that very often because, well, we don't use the English system of measurement for science very often anymore. but engineers used to use slugs all the time. All right, weight, on the other hand, is the downward force due to the pull of gravity on an object's mass. And weight is, again, it's mass times gravity. The unit for weight in the SI system would be newtons. In the English system, it would be pounds. So a pound is a unit of force. Okay, so you can measure, we usually think of weight as being a downward force because that's where gravity pulls on our mass. So we usually think of pounds as being units of force going downward. But actually, you could measure forces in any direction in pounds. If you took a bathroom scale and hung it on a wall and then you leaned against it, it would read, it would give out a certain reading as a certain number of pounds. And that would be the number of pounds of force going sideways. So a force doesn't necessarily have to be downward, even when you measure it in units like pounds. And you could certainly measure a force going sideways in newtons also. Okay, remember that forces are vector quantities. They have a magnitude and a direction. For example, for weight, the direction is downward. But for other forces, the direction, there could be any direction, but, there is a direction. So weight being a force, weight is a form of force, and that's a vector. But mass is a scalar because there's no direction associated with it. Okay, so also under weight, for any given object, I said this, but not quite in these words. For any given object, weight will be proportional to the force of gravity on whatever heavenly body you happen to be standing on. Because for any given object, the mass will be a characteristic property. It won't change. So if gravity changes, then the mass changes. On the other hand, if you're staying here on planet Earth, gravity will be constant, more or less, and so weight will be proportional to mass. Okay, so as long as you stay on Earth, weight is proportional to mass, but if you're moving around to other planets, then weight will be proportional to gravity. Basically, weight is mass times gravity. Whichever one of those is changing, mass or gravity, weight will be proportional to that. If they both change, then weight will be proportional to the overall change in the two quantities. Okay, so we could look at an example. If the weight of an object on Earth is 64 newtons, what is its mass? Well, weight is equal to mass times gravity. Here, if you want to rearrange this equation, you can put it into one of our little triangles. Weight is equal to mass times gravity. So mass, it's mass times gravity, so they have to be next to each other in spaces in the triangle, and that leaves weight for the other one. So weight is mass times gravity. If we want mass, we cover up m in the triangle, and we see that mass is weight over gravity. Okay, so the weight is 64 newtons, and gravity is 9.81 meters per second squared, and 64 divided by 9.81 is 6.5, and that will be kilograms. Now you might wonder how you get kilograms out of these units here, and that's because, remember, newtons is actually kilogram meters per second squared, and that will be over meters per second squared. That's equivalent to kilogram meters per second squared times seconds squared over meters. So instead of dividing by meters per second squared, we're multiplying by the reciprocal. Notice that seconds squared cancel and meters cancel, and look what you have left, kilograms. So it does actually work out. Okay, it's a good idea to be able to work the units out like that, just to make sure that you're arranging things the right way. Because if like I've said, if the units come out correctly, then the number's probably going to come out correctly too. Okay, that's about 30 minutes, so I'm going to cut part C there. Because we're into the physics section now, and there's a lot of material to cover, and the lectures won't go as fast compared to the way they do in person as they did before, because when I teach this class in person, when we're doing the math section anyway, I'll often set up a problem and then give the class several minutes to work it out, and then we'll come back together and compare results. Well, doing it on the video, I was assuming that you were pausing the video, so I wasn't actually waiting. And so things went a lot faster on video than they do in the classroom. That actually won't be as much of a factor in the physics section of the course. So what I'm getting around to is that we're going to be going back to 4 segments for each lecture, or in other words, 2 hours per lecture for the physics section, at least until I see how fast things are going. If things keep going a lot faster than I expect, then maybe we'll cut it back down to 3 segments again. But for the time being anyway, we're going back to 4. So there will be one more segment to this lecture, and that'll be coming up momentarily.